the last 2 minutes.
Okay, thank you. I will start the presentation. Hi, my name is Yeji Hong. I'm a PhD student in the Department of Civil Engineering at Purdue University. My presentation today is about generalization of construction object segmentation models using self-supervised learning and copy-paste data augmentation. This study was conducted jointly by 4 people. A second author, Yeji Chern, is a PhD student at the University of Dayton. The third author, Nguyen, is an assistant professor at the University of Dayton. Lastly, a corresponding author, Hongjo Kim, is an assistant professor at Yonsei University. I'd like to start with an introduction. So, computer vision technology has been widely used to analyze job site context from construction site images for safety management. For example, by identifying workers and their personal safety equipment, we can determine whether the workers comply with safety rules for construction tasks. Convolutional neural network architectures show superior performance in visual tasks than other traditional recognition methods due to the capability of learning visual features from training data in a supervised learning manner. However, supervised learning models generally perform well on data similar to training data, but typically do not work well on unseen data. For example, the semantic segmentation model in a supervised manner trained with the left side scene achieves low performance when it is tested with the right side scene. Let us call left side data as source domain and right side data as target domain. To make a semantic segmentation model perform well without target domain data annotations, we propose a domain adaptation method that includes 2 main components. The first one is domain adaptive segmentation with self-supervised learning, and the second one is copy-paste data augmentation. Let us move on to the methodology. The domain adaptive segmentation includes 2 steps. The first step is to train a segmentation model using only a source domain data with annotations. And the second step is to adapt the model to a target domain data. The second step contains pseudo-label denoising and target structure learning using prototypes. Prototype is a representative feature that is mean feature of each class as seen in the figure. Because we do not have any annotations of target domain, we use the decision boundary from source domain data. But wrong pseudo-labels exist because of the domain differences as the yellow area. The distance between each feature point and the prototype is inversely multiplied by the conversion equation to make the pseudo-labels accurate. Pseudo-labels are adjusted and prototypes are newly calculated after each training batch like this. The target domain data is dispersed in the feature space because of the domain gap. It hinders the pseudo-label denoising, so the aim of target structure learning is making more compact target features, as you can see in the figure. Pseudo-label denoising and target structure learning was proposed in the reference below. Training data with various visual features helps to avoid overfitting and to generalize deep learning models. To increase the visual diversity of the training data without annotations in the target domain, we employed a copy-paste data augmentation method. Let me explain the copy-paste data augmentation framework. First, one of the target domain images was randomly selected And second, the area containing the foreground was removed manually. Lastly, instances from the source domain data are pasted into the background of the target domain. In this way, deep learning models can learn the features of the target domain background and the diversified boundaries between the foreground and the background. We are using deep domain adaptation index for intuitively evaluating the domain adaptation performance of segmentation models as shown in the equation. This index evaluates how well a model performs on the target domain without annotations. When domain adaptive index value is 1, the domain adaptive model achieves the same performance as the model trained with the target domain and their annotations. In this study, 1 source domain dataset and 2 target domain datasets were used in experiments. All datasets were collected from 3 videos of scaffold installation site at Yonsei University located in Seoul, Korea. Target domain 1 differs in scale from the source domain, and target domain 2 differs in the worker's appearance and the background. This is the experimental results for target domain 1. The results show that the generality of the segmentation model was improved. As shown in figure C, the model only trained with source domain data incorrectly predicted a large number of pixels in the background as the worker category. And looking at the figures D, the noise was partially removed by the domain adaptation strategy, and it missed a part of hard hats. In figure E, we can find the copy-paste model well identified the worker's arms and legs and all the hard hats. This model achieved the highest domain adaptation index, which is about 81%. When domain adaptation and copy-paste methods were applied together, as you can see in figure F, we lost a few hard hats and a part of shape of the workers. The IOU of hard hat reduced by 4% points due to the loss of hard hat pixels. Both two strategies improved the performance of identifying workers. Although the IOU of hard hat decreased, the domain adaptation model and copy-paste model found the accurate place and the accurate number of hard hats. Therefore, we expect that we can use these models for safety checks by using image processing methods such as a morphological analysis together. Let us talk about the result of target domain 2. Target domain 2 has considerably different visual characteristics from the source domain. Mean IOU has improved by 28% points when the domain adaptation and copy-paste strategies were applied together. The model achieved about 85% of domain adaptation index. As you can see in figure C, the source-only model misidentified many background pixels and estimated the white object on the ground as a hard hat. When the domain adaptation strategy was applied, the model removed the part of misclassified noise, and the copy-paste data augmentation strategy strongly improved the segmentation performance, as you can see in figure E. Only real workers and hard hats remained. It is conjectured that the copy-paste augmentation contributes to recognizing target domain background features. When the domain adaptation and copy-paste are applied together, The IOU of hardness slightly decreased. We think our method is sensitive, especially for small objects such as hardness, so fitting more distinguishable features to the model is required. Considering this, we plan to additionally apply the augmentation methods to small safety equipment. This is the conclusion of our study. This study aims to increase the generalization capability of a semantic segmentation model for workers and hardness. To address the generalization problem, a self-supervised learning-based domain adaptation and a data augmentation method were experimented for scaffolding installation site images. The proposed methodology showed the potential of generalizing a semantic segmentation model without additional annotation efforts. Future studies will be conducted to reduce the remaining gap between the highest mean IOU of the proposed model and the upper bound model. This is the end of my presentation. Thank you for listening. And if you have any questions, please ask me.